Okay. Hello everyone. So I'm the one between before cut it off from the rest. Okay, have a break. So hopefully I'll get it quicker. And thanks a lot for Avin Kula talk about a lot of interface using the AFM and for the chemistry and moleculars. And that's really amazing. And thanks a lot for Dr. Tao talking about the really emerging questions. So I confess I need to be more use less plastic bags. Okay, so I try to use every time I go to market, I try to use the sustainable or a permanent bag to myself. Sometimes I forgot, so I waste a lot. Okay, the plastic bags. So we start from ourselves. It's good. So okay, today my topic is about AFM-based nanomachining. So my topic specifically is using external energies to assist the nanomachining process. So for today, I'm going to cover the topics about using AFM-based nanomachining assisted by ultrasonic vibration only by the mechanical vibration. So I'm going to show the setup, mechanism, and the results. Also, I'm going to talk about the current update. We just published a paper about the using the two different energies, ultrasonic vibration and the gel heating. Okay, and so I'm going to show the setup and the results. So first of all, because we know I don't need to emphasize too much about the importance of the nanometer scale. As for advanced manufacturing area, so those are nanofabrication techniques that are being used for chemical sensors, energy storage, semiconductor, optical, and biomedical devices. So because of all those advanced nanofabrication techniques, we enable those applications. So basically, the photolithography has been a huge success in semiconductor area. And in terms of going on, so the EUV is coming through, right? So it's the next generation. And the X-ray is one candidate, but it's not that popular. So besides that, electron beam lithography and ion beam lithography, so they use electrons and ions to create patterns on substrate, and in order to create patterns and advanced manufacturing technique. So AFM-based nanolithography. So there is a role for the AFM-based because of its easy to set up and very popular and has been studied a long time. And it has a real kind of maskless and low-cost space. And we have a lot of course, because of Park system, this AFM has been advanced a lot. So let's talk about the pros and cons of those advanced manufacturing or nano manufacturing techniques. So the EUV and X-ray, they are high throughput, high resolution, but they require mask, just like photolithography, right? And E-beam lithography and ion beam, they are maskless, okay? They are high resolution and high versatile, but the electron beam, they actually, because of the scattering, forward scattering, backward scattering, and the low throughput, and also expensive, they have some disadvantages or limitations. Similar like ion beam. So ion beam that has besides the ion milling, those preparing samples, it can also do lithography to do preparing some nano manufacturing techniques. Because of the substrate damage, low throughput, and also it's very expensive. So for the AFM-based nano manufacturing, the AFM is way cheaper than the electron beam or ion beam system, and it's also versatile. It can really achieve in the few nanometer scale, especially for the STM, right? It's really high resolution and advanced. So there are some limitations. So large force, if you want to really create some nano patterns, traces, or different surface geometries, it is really because of large normal force. We have to apply a lot of force. We use a traditional AFM tip. Or because of the large force, the tip has gone very quick. So we got to keep replacing. If we want to really use this for let's say, for a mask manufacturing for photolithography or for other things, so the mask fidelity may not be maintained very well because of tip work, because of large force. So what we want to do is really overcome these barriers and try to improve the tip-based nanomanufacturing. So first of all, I want to talk about some 3D nano fabrications. So because of 2D is really being invested a lot because photolithography, all those 2D features. So because 3D has its own role in terms of advanced techniques. Let's see the optics. Let's say, for example, one very interesting application is they're trying to focus the lasers from the 5 micron the diameter into a 1 micron diameter. So they fabricate using the focused ion beam, milling a mold, and then do the PDMS on the surface, and they got a very focused laser beam. And then plasmonics. So let's say the SGRS substrate or bio-nano devices, three-dimensional shape or the devices play a very important role. So today I'm going to talk about the external energy assisted way in terms of 3D shapes. So we just talk about electron beam, ion beam. So they are capable to do some 3D shapes. So for the 3D shapes, the electron beam used the typical way, like changing the exposure, changing the dose of exposure. Let's say if the dose is really large, after development, you can see all the areas being gone. So let's see this area. And also, if we gradually increase the dose, you can see there's actually a stair-like shape will be developed after finishing the process. So as we just mentioned, because of the electron beam lithography has its own limitations because of the forward scattering and the backward scattering. Forward scattering is because the electrons are really light. When it bumps into the materials, it tends to diffract. It tends to have some random diffraction. So then the features actually become larger. So that means you cannot go that much deep, and because the feature is going to be out of its original dimension and become considerably large. Also, like the backward scattering, because substrate, you can backwards and increase the manufacturing resolution. So you can see, like those are simulation results from one research group. They simulate the electron beam results using the high voltage. You can see electron beam actually goes gradually, randomly scattering around. And if we use a very small electron beam, it goes very small, but it's hard to tune the dosage, right? And also some other like ion stuff has its own kind of very irregular traces. So that means we want to really do three-dimensional stuff. So it has its own limitation. So when we talk about AFM-based 3D nanomachining, it has own advantages besides the, let's say, not that expensive or easy to set up. Another advantage is actually we can get a positive draft angle naturally from the tip shape, because the tip shape is looking like this, right? So when we actually do a mold out of the surface, so if you want to do a kind of continuous patterning or use this mold for many patterns, so the shape is like just similar like we do a traditional casting process. So the positive draft angle help us easily demold the whatever we want to do. So that is different from the shape of the electron beam. This is actually the shape we got. So if we do this and try and do the reverse modeling, we got a problem getting the molds out. Okay, so this is another advantage besides the easy setup, low-cost stuff. So that's why we're trying to do something out of directly using the tiny tip over here. So traditional AFM-based nanomachining, so some researchers directly using the tip, right, and apply the force and then get trenches. However, because the trench is not tunable, and because the trenches we need really large force and to really apply the tip on the surface and penetrate it into. So that is a limitation in terms of force and the tracemark stuff. So this is a setup we use to actually make the nanomachining process easier and high throughput. So what we do is we actually integrate a customized nano vibrator. We call it nano vibrator, integrated with a Park System XE series AFM. Is commercial, but this is all fabricated in the lab. So we have X piezo, Y piezo, and we have pillow. So because of X and Y piezo, when we send out the solenoid signals with 90 degree of the phase difference, it's going to be a circular when it's vibrating. Okay? And then there's a Z piezo. We are placing it on the top of the pillow, and on top of Z piezo, we place a sample. And sample we use as a PMMA here. So when we use a very stiff, like type 190 DLC, a diamond-like carbon tip, so the tip can penetrate into the surface because of the Z vibration. And we're going to show some data, of course, and results. So input the signals with a different frequencies. Actually, we can tune the frequencies based on the needs. So 2 kHz is what we usually use. And then generate circles. And this is the entire setup. And the Z signal we use is actually ultrasonic, 2 MHz, directly applied to the Z piezo, so you can vibrate up and down. So the mechanism I just mentioned briefly, and I'm going to talk about the tunability of the process. So because the tip shape is a tip, if you use a knife or a pen, scratch on the surface, the size is going to be exactly the size of the pen or the knife. But if we have the vibration, so the vibration R is a small, is the radius of the tip. And the red R is the vibration amplitude. So because of the XY vibration, the stage is actually vibrating in a circular way. So when a tip going down, attached on the surface, you can see this is the outside blue circle is the actual the tip traces or the mark size we can generate. So because we can easily tune the vibration amplitude by changing the XY by changing the voltage. So that means we can easily tune the width of single pass trenches. That is the function of XY vibration. And in terms of the Z vibration, so we have the high ultrasonic vibration, the piezo, because the tip is itself has very high vibration frequency. So it usually is 160 kHz. So that's very, very high. In order to make the tip kind of freeze in itself, the frequency has to go way larger than the resonant frequency of this tip itself. So when we use 2 MHz frequency in the Z direction, so the tip is actually freezing in its original place, other than vibrating up and down. If any vibration frequency lower than the resonant frequency of the tip, so tip is going to just vibrate along with the sample without too much indentation. So because of the Z vibration, okay, so we can dynamically freeze the cantilever, and the cantilever can penetrate into the sample and create those patterns. So this is it shows some nanomachining capabilities we have. So this plot shows because we can easily tune the XY vibration amplitude. So the trenches, so single pass trenches machining. So the single pass, we can easily tune the width of single trenches. So that's what we got. And because of the XY vibration, and also we have the Z vibration. So the Z vibration, we can tune the depths of the nano trenches. So that we can see if we have the Z vibration amplitude gradually increase, but we set up a design. Let's say I want this tip go down 20 nanometers, but if I increase the Z vibration amplitude, you can see the actual depth of the single trenches is actually increased with the amplitude. So also, if we maintain, let's say we maintain 2.5 volts, okay? So there is a certain gap between the design and the actual. So let's see, I design 15, let's say 15, so there's a certain depth after maintain the certain amplitude over there. So if I design 15, 20, 35, gradually you can see with a certain Z vibration amplitude, the actual depth is actually followed very well. along with the designed depth. So because of in the XY direction, the in-plane capability, as well as the Z direction capability, we can get three-dimensional stuff. So this is the pattern of my PhD school, North Carolina State University, the IC department logo. So we actually input in and get a 3D shape. So because of the capability, okay, so we can get a lot of applications out of it. So one specific thing is the 3D nanomodes. Currently, people talk about scalable nanomanufacturing because we can have a mask, and then we can gradually go to scalable. So one possible way is using the molds. If we have molds, we can do stamping. So easily do stamping, and then we can duplicate a lot. And so we actually fabricate based on the original input. We fabricate those 3D nanomodes just like stamps. So you can see this is the first layer. After the first layer, we have a few circles. So those are the actual depth is about 80 to 90 nanometers, depends on the design depth and along with the Z vibration. So this is the result. So after we get the 3D nanomodes, we can actually use the PDMS to do the reverse casting, and you can see it is pretty much maintain all those shapes. And then you can see we did some more patterns with different depth, and also after the molding process, it actually duplicate those pretty well. So some those are the reverse modes fabrication. So after that, we try some soft lithography process, because the modes after fabricating the modes, we're actually trying to get the same geometry, right, out of the reverse mode. So we have many soft lithography techniques. So we're trying to combine those techniques with this 3D nanomodes. So we can actually do UV curing, just pouring on the molds, and then get a real a similar original directly out of AFM. But we actually tried another thing that is usually tried in 2D. I don't see too much try this semi-process in 3D. So we're pretty interested in this process. So the process is actually, we got the PMMA coating on a silicon substrate, and the coating get patterned out by the AFM-based nanomachining. So it looked like some patterns like these, ASCII or nanomodes, and then we got a PDMS, right? So we have PDMS, then the solvent assist micromolding process is actually using the acetone or any chemical solvent that can actually solve the PMMA surface. And then because of applying against the mold, just by pressing on the mold, we got original shape directly out of the AFM. So it's much quicker than after doing the 3D nanomachining, right? So this is the entire process. So this is the results we got. Actually, it's not. You can see the overall shape. It is fine. We can see 3 layers, a square, and inside cylinder shape. But it turns out because there's some we actually press it manually, okay, without too much control, and also the PMMA thickness is not that high enough. So we got not a very good shape out of the in terms of the depth and the fidelity by replicating. But this process can be further improved by increase the PMMA thickness or the process, by optimize the process. So we talk about the applications, right? So what is the quality? So the quality is important, even though in nanoscale would actually tend to be replicated in so many times. So the quality can be maintained, or say manufacture those really high usable sensors or some other functional device. So this is another result showing the original Steve Jobs, and then we got a 3D shape out of the surface. And then I compare the original cross-sectional profile with the non-machine cross-section profile. So you can see the dotted line is the original shape. the solid line is the shape after. So you can see there's a lot of difference in terms of, especially at the bottom area. Let's say for this blue line, so you can see there's a deep change. But as we know, because of AFM, it has a kind of reverse pyramid shape. So it cannot do, basically it cannot do a vertical shape like this. So this is one limitation, okay? And also there are some very sharp, even though it is sort of reverse the pyramid, but because of limitation of the tip, as well as we actually increase the tip size. So that means we actually sacrifice a little bit of the resolution during the nanomachining. So you can see some of the details we're losing, even though overall it looks similar. So this one conforms very well in terms of this deep change. But the very high frequency change, it has a little bit different stuff. You can see there are some of differences in terms of the quality. Okay, so because of this, sort of one reason is because of the embedded reason. I just talked about the tip. Okay, the vibration reduces, limit the resolution. Another reason is actually the tip life we just mentioned before. The tip can be used only for a while. Let's say for this pattern, maybe for 5 patterns, 10 patterns, is gonna severely wear. So the fidelity cannot be maintained all the way along this 5, 10 patterns. So that is another limitation we have for this process. So I came up with another idea, just trying to increase the lifetime of the tip to make the pattern more consistent in terms of making more patterns. So then we have because we already have the XY vibration. I trying to make it larger so we can see clear. We have a jaw heating thermal element between the sample and the XY vibration. So because we have a jaw heating, we can see the temperature can go 25. It's actually can go up more than 100 degrees C, but I don't want to destroy the AFM. So doing experiments, we're trying to set a lower temperature first and gradually go up. So even though we can go more than 100 degrees C, but trying to limit the stuff. And we can see even increasing from room temperature to 45, we got a very different results in terms of the trenches. And actually another thing I want to mention is the tip. So originally we used the ultrasonic vibration assisted process. So the tip has to be DLC, has to be very stiff. However, when we use when we incorporate thermal in the process, so the tip can be used, is very small. The spring constant is very low. The good thing about the low spring constant is it actually, because of some sharp tips, okay, they usually contact tips, they have sharper tips. And for DLC coated, they usually have larger radius. So one advantage using the small spring constant is we can get the sharper features. And another thing is if we use high spring constant, the resolution of the force is being very low because the signal will just have a same signal, same laser, but the spring constant, if we want to have 10 nanometer difference, it's very hard. But this one we can even achieve a few nanometer difference. So that'll give us more resolution in terms of applying the force. So we use a soft tip, and it turns out without any vibration, it is very hard or impossible to create any trenches. Okay, almost impossible. But if we add some vibration along with the thermal, it works. So if we only use the thermal, not saying that the trenches, but the adhesion force, that really play a very important role in terms of manufacturing process, because adhesion will actually bending, because tip is very soft. It can bend in it around and make the very not irregular trenches. So the vibration actually decreases the adhesion force a lot. That facilitates the nanomanufacturing process, nanomachining process. You can see that is the without vibration and with vibration. And we measure the adhesion force. So you can see is very consistent after applying the vibration. So there's a lot. So it's a very good marriage between the vibration and thermal. So as you can see, because we can use very small force, the trenches we can go from a few nanometers all the way to 10 nanometers, and we can go higher if we use a very stiff tip. So the force we can apply the minimum. Actually, nowadays we can apply only 50 nanonewton, so we can create 10 nanometer trenches. I would say it is very hard for other techniques. And now, besides that, we use so we designed a two-level factorial design, and we can see using the small force and small vibration amplitude, the trench depth and the width, both of them are very small. And if we increase the force only, the depth doesn't increase too much because the tip is pretty small. The tip is pretty low spin constant, even though we almost double the force, so it doesn't increase the depth a lot. However, if we can see, we use the same force, compare A and C, but we double the vibration amplitude. So the width is increased a lot, and interesting is the depth actually increased a lot. So that helps the manufacturing process a lot. And so that is another thing. So we compare the force with larger vibration amplitude in the XY direction, and we can see the force doesn't help that much. So that means when we're just using a very small force, using this external energy-assisted nanomachining process, using vibration and dual heating, so even we can use a very small force, the trenches can be fabricated. Okay. So you can see this is a 50. We use a 50 nanonewton force using a very soft tip. So you can see this is the results. About the 7 nanometer uniform trench. So this is the cross-sectional profile from this depth of the trench, and this is the green line shows the trench shows the profile of these 3 trenches. Okay. So the result shows the soft tip. Even use soft tip, very low force, 50 nanonewton, we can get 7 nanometer trenches. Okay, so the summary is, so we actually present results from only use ultrasonic vibration. Okay, it turns out the tip, okay, it can work, and it works beautifully, but the tip won't last long. So as we know, if we actually use a little bit larger, a little bit higher temperature, just a little bit, from 25 to 45, it can rapidly decrease the needs for the force. Okay, originally we used maybe hundreds of nanonewton, 300 at least, so we can get it similar. But now we can use 50 nanonewton. As we know, lower force always associated with lower tip wear. And then, so another interesting thing is the vibration amplitude has major impact on both width and depth. And some other results I haven't put it on here is we're actually using different tips. So like soft, medium soft, and very high spin constant tip. So it actually, we use the same 50 nanonewton. The results is entirely different. We haven't finalized the results yet. I didn't have too much, but it shows the stiffer tip will have larger depths, even when we use the same 50 nanonewton. So that's another interesting result. I haven't finished up that experiment yet. So I think that's all for my today's presentation. Thank you. Yeah, just let me know if any questions. Yes.
Just 2 short questions. What are your tip materials, and also what are your substrate materials?
Yeah, the tip material, the soft tip is just silicon itself. Okay. And the hard, very high spin constant tip is DLC, diamond-like carbon, okay. Coated tip.
And then the
substrate is the polymer. I would say any polymer. So now we use is PMMA.
So the glass transition of the polymer is also very important.
Yeah, glass transition usually is about 100. For example, PMMA is about 100, 105. Mm-hmm. So it is.
Yeah. Have you looked at thermoset materials like epoxy? Or
we haven't looked at it yet. And also very interesting is the rubber kind of like material. We haven't tried. This is a very interesting material we can try. Thanks. Yes.
The throughput of this thing, and how long would it take you to make anything of a sort of industrially useful size with a single tip, or is there a way of multiplexing? Or?
Yeah, so for one pattern I showed, maybe the the Steve Jobs, maybe you remember, or the ICE, they are about 2 by 3 micron. So they typically spend 15 minutes to 20 minutes to finish up one 2 by 3 micron size. Depends on your size you need. But actually, when we do experiments, the setup time is much more than the machining process.
If you were comparing it to kind of lithography that I guess is used in semiconductor industry, and are you putting millions or billions?
Yeah, millions or billions. Yeah.
How long would that take?
That will take forever, obviously, for the AFM. So even though for the photolithography, the electron, those stuff, they need a mask. So this is a technique for making a mask, or for just like an electron beam, usually for making a mask. So so another way to mass produce is using the molding process. To use like what I showed, the PDMS. So if we have a high quality mold, and then if we further improve the demolding process, so you can see just by stamping, we can create those duplicated patterns. But of course, it won't compare with the currently very efficient photolithography. So that is a parallel process. This is still a series. If we only use the AFM, it's still just like an electron beam. It's a serial process. Yeah, thanks. Yes.
I'm curious, why when you use the vibration, the adhesion forces decreases?
Yeah. So to my understanding is if the temperature increases, the adhesion force increases. But if we use the vibration, the detachment between the tip and the surface will be much easier. So you will see the small trenches we get at a very low force, and it can get some trenches because of the decrease of the adhesion force. But why? I think it's because the vibration that can rapidly detach the tip with the material, even under elevated temperature. Yeah, thanks.
We are supporting some customers who are trying to use our AFM for mask repair. And the challenge there is to basically doing nanomanipulation, moving nanoparticle one place to another. The name of the game is to use a minimum force to do that, so that we don't damage the very expensive mask surface.
Okay.
Have you tried this technique, vibration technique, or assist technique for nanomanipulation?
At the very beginning, we tried manipulation. We tried to use the ultrasonic vibration to cut nanowires to do some destroy, not repairing. So we're trying to destroy. So for example, if we want to cut a, let's say, nanowire of silver nanowire. So previously it's very hard. Like it takes multiple times, and the force is required. But with the vibration, we can cut the silver nanowire with a little lower force. But in terms of manipulation, for moving particles, we haven't tried that yet. So, but we tried move it only with the small force in the Z vibration, and the Z vibration actually decrease the adhesion force a little bit. But we haven't finalized do a systematic research on it. We did some pre-trial, so we don't know too much about the actual application as you mentioned. So we actually, because the Z vibration actually decreases many of the adhesion force stuff, so we can push it a little bit. Yeah. So I haven't do systematic stuff on that. Thanks. Yes.
It's very impressive results. I have two questions.
Yeah.
One is I noticed the patterns have there are trenches, but there's also stuff on the side of the trenches.
Yeah, on the side of trenches.
Have you tried, say, post-processing?
Yeah. Well,
Is the material modified such that their solubility changes that you can remove those materials? That's question number one. The other is for the diamond-like carbon. No.
Diamond-like carbon.
Have you tried like fluorinating the surface, making whether that would make it last longer or have different or better machining performance?
Okay, so thanks. First question, we have, those patterns you see, the Steve Jobs, the ICE, those 3D patterns, actually after directly finishing, there's a lot of debris covered on the surface. So we have to do post-processing to wash it away. So currently what we do is using 30% acetone and aqueous solutions, so mixing acetone with water, and 30% we're using ultrasonic agitation, we wash it away. Another technique we use is we cover a 10 nanometer sacrificial layer. So we penetrate like a PEO surface. So PEO is quickly water soluble. So we coat a 10 nanometer on the PMMA. So after penetrating all the way through the PEO and the PMMA, it's been, you can take away, actually become more clean than just directly using acetone solution to wash it. So not a sacrificial layer. So we basically use two techniques to do this stuff. And is that enough for the question? First question? Okay. The second question is, I'm not sure how to modify the tip, because you usually just buy the tip from the manufacturer. So I think this is a very interesting question. So
You can try a CS4 or SM6 plastic.
and make it more functionalized.
Just fluorinated.
Okay. Okay. Just formulate.
It doesn't stick to anything. Not even adventitious hydrocarbons.
Oh, that's interesting. Yeah, because we have a lot of actually debris attached on the surface, so and tip stuff. This is maybe another useful. I'll look into that. Thank you. Yeah, another question?
All right, thank you.
Okay,
I
thanks.
think we're still going to try to sneak in a short morning break.